Greetings, the Astro 30 here yet again, and today, before I pull the lab apart and pack everything up ready to move in the next couple of days, I thought I'd make one more video. And today I'm going to look at something that I actually found randomly on the internet. It's apparently supposed to push 260 watts RMS into an 8 ohm load. Now, looking at the supply voltages of this amplifier and the overall topology, that is generous, say, to the least to say that. I doubt it would get that high. Now, two things. The output stage here, which is actually in Darlington configuration, these transistors, the TIP140 and the TIP145, which are not easy for me to obtain, are actually Darlington transistors themselves. So we've actually got two Darlingtons in parallel with another Darlington driver. The supply voltage is plus minus 45 volt. Now, assuming this amplifier could produce an output voltage of roughly 80 volt peak to peak before clipping, if we do the math on that, at peak, that's 200 watts into an 8 ohm load. Using the RMS voltage value, that's 100 watts, but it's nowhere near 260 watts as purported. Now, instead of these Darlington transistors here, I'm going to use a TIP3055 and a TIP2955 respectively. But we're getting a little ahead of ourselves here. Let's go through the circuit description a little bit better here. Over this side we've got our standard long tail pair input stage. This is comprising of two BC556C transistors. And what's interesting here is each emitter has its own 270 ohm resistor here. And then it goes into a 12K resistor up to here, which is part of the positive rail. Now, what this is an attempt to do is to try and balance the input stage as best as possible, also matching the HFEs of the transistors together so that they're roughly similar also helps, and that's in an attempt to try and lower the overall DC offset at the output. Now, the one side of the transistor long tail pair here, we've got a 1K resistor at the input, 100 picofarad ceramic capacitor here, and this attempts to stop any RF or high frequency getting into the amplifier and being amplified. Going through a 220 nanofarad polyester type capacitor here as the input capacitor with a 47K input resistor. Now, when I say input resistor, I mean ground reference resistor for this transistor. In the collector of the first transistor we have a 680 ohm, we'll call it a degeneration resistor, but we have a 680 ohm there and a 47 nanofarad going to ground hanging off that. That's just to act as a filter for any high frequency noise that may be on the power supply lines. The other side of that resistor then goes off to the base of this BD139 transistor, which is our VAS stage. Over here is the other side of the long tail pair, which the feedback from the output comes back into its base. So the gain is set by this 33K resistor and this 2K2 resistor respectively. Now, with these values here, we're looking at a gain of roughly 13. And that's just at a guess. So let's do the math. Divided by 2.2 plus 1. It's actually a gain of 16. I think I said it was a gain of roughly 13, 14. I was close. Anyhow, so with these two values here, we're getting a gain of 15. What's interesting up here is we've got another 680 ohm resistor coming in series with the positive power supply rail, going through this 1N4001 rectifier diode before this 12K, 270 ohm string. and we've got a little 100 microfarad 50 volt filter cap here. What this is an attempt to do is to isolate the input stage from the supply. That is, we're basically decoupling the input stage from the rest of the amplifier, which is okay and is quite a standard thing to do. And the same is also true here just before the VAS. We've got a 100 ohm resistor here on the negative supply line, which is separating that half of the circuit from the output stage. And with the VAS here, we've got a 47 ohm emitter degeneration resistor there. It can, just for all intents and purposes, be connected directly to the negative supply. So following the VAS, we go into this rather convoluted looking biasing network. So we've got a 2K7, a 3K9 there, which is on the base of this first driver transistor, which is a BD139, which has a 120 ohm emitter degeneration resistor between that and its output. Then that goes through an 82 ohm into three 1N4004 diodes. These three diodes must be in contact with the output stage transistors or the heatsink so that it can adjust its the current in the output stage accordingly as the thing heats up. Because the more these diodes will heat up, the more they'll conduct, the more voltage will flow through them in the theoretical sense. This here is basically a voltage divider, and this cap, which is an interesting value of 270 microfarad, which not since the 80s have I ever seen a value that's that strange, so I've marked it as 330. This is a bootstrap, which is basically giving the output stage a constant current source, and interestingly also it's bootstrapped down here as well. So you can bootstrap it either to the negative or to the positive, it makes no difference, but it's got two bootstraps by the looks of things here. And of course the end of the diode string here goes into a BD140, which is the other driver. This output stage then is connected in Darlington configuration, and then these two output devices are connected in parallel with each other with their own separate degeneration resistors. In this case we're looking at 47 ohm. I reckon that's a little bit too high, so I'm going OR47, which is 0.47 ohm. 5 watt is fine. Now, I don't know what the hell's going on here, but for some reason he's got a 10 ohm 5 watt resistor as part of this Zobel network here. It doesn't need to be that high. 1 watt will suffice, so why have another large device on a PCB except to take up PCB space? And the other interesting thing is we've got this lonely 10 ohm 5 watt resistor in series with the output and the speaker just hanging out in the breeze doing nothing. Not sure what the purpose of that is. Normally if you have a 10 ohm here you'd have a coil or inductor in parallel with it, and that's used when you're driving capacitive loads so that the thing doesn't go into ultrasonic oscillation and all that sort of thing, causing the output stage to heat up and go into thermal runaway conditions. But on its own, it's not really doing anything, except the only thing I can think of why it's there is in case this output is shorted to ground, well then most of the current is going to be flowing through this resistor. Because as voltage works, it will look for the shortest path to ground, and this 10 ohm resistor, poor 10 ohm resistor, would be the closest, shortest path to ground rather than going through the output stage transistors and destroying them. Yeah, but running at plus minus 45 volt here going across this 10 ohm resistor during a short circuit, yeah, at any one time you're going to have at least 40 volt going across it. That's a considerable amount of current going across that one resistor. So to work out the current of that, it's the voltage divided by resistance. So say it's 40 volt roughly going through there in a short condition. Divide that by its resistance, which was 10, equals, well, 4. So there's going to be 4 amps going across that resistor, and it's only rated at 5 watts. So to work out what the power is, we need to take the voltage multiplied by the current. So we multiply that by 40. That's 160 watts of dissipation. Yeah. So yeah, having 160 watts of dissipation across that 5-watt resistor is not going to make it very happy, let's just say that. And I'll put a link in the description to where I got this from, but here above it is the proposed power supply. You're looking at a 32032 transformer, which I've never seen one. Not in toroidal anyway. I'm not even sure how old this circuit is. But it's 32 volt plus 32 volt at 4 amps. So the transformer needs to be capable of at least 4 amps in this configuration. I doubt that this amplifier is even going to get anywhere close to 100 watts. Let's just be fair. Now, would it make a difference if I substitute the output transistors for TIP 2955 and 3055 respectively, compared to having Darlington transistors here? Well, it's all about current. Now, the Darlington configuration is good at producing high gain and high current capabilities, which is why it's used. So, if you're using just a standard transistor, not a Darlington, well, the TIP 305 and 2955 respectively have around about a maximum current dissipation of 5 amps. So looking at these, I believe from what I read of the specifications, these TIP 140 and TIP 145 have a 20 amp current dissipation. But considering that the power supply proposed for it is only designed to provide 4 amps, there's no need for large Darlington transistors like that as the output stage. But rather than just talking about this shit, why don't I just build this up on breadboard? The output stage from here back will be built on the heatsink with the resistors soldered to the transistors and wires and shit, and we'll delete this 10 ohm 5 watt resistor, as there's no point to it, change that to a 1 watt resistor for 10 ohms, and I might have to make a substitution somewhere. I'm pretty sure I saw 120 ohm, which I don't have, but for the life of me I can't see it now, so it's obviously not relevant. I must have been looking at a different circuit. Oh well. So yeah, I'll build it up on breadboard and we'll run some tests on it. So when we come back, I'll have this all breadboarded out, and yeah, hopefully it works first time. I'm going to leave the gain alone at its gain of 15, which seems a little bit low, but I'll leave it at the values alone. The age values I'm changing are these output the generation resistors to 0.47 instead of 47. It shouldn't make that much difference to it. Anyway, so I'm going to build this up on breadboard and we're going to come back and do some tests on it. Okay, so a short time later, about 20 minutes or so, I've got the input section only built. So I've just got this section built here. I've got an oscilloscope connected to this collector of the first transistor as the output. That's before the VAS. And I've got a 47k resistor going from the base of this transistor to ground, the same as it is over here. So with it operating at about plus minus 15 volt, I'm going to turn the supply on and see if we get an output signal. Yes, we do. Now, albeit we can't really see it. Now I've got 1 volt 1 kilohertz going in, and I've got less coming out than should be going in. That's kind of interesting, isn't it? So I was expecting that to be a little bit higher, definitely on ×1. So at half a volt per division, I'm getting a peak to peak of not even a volt. So I'm actually experiencing a loss. I just wonder if removing this second ground reference resistor will affect it. Well, yes it does. We now have absolutely no output at all. With that resistor on the other base, that 47k disconnected from ground, we get no output. But if we now connect it, we have an output. As to what happens when I move the input lead from where it is to the base of the other transistor, so I'll just remove that lead And I'll just touch it to this 47K. We don't appear to have anything. Let me put it through a cap. So if I put it through a capacitor, we can see we do actually have an output now on the other side. And if I connect it back to where it was, we got the same output on the other side. So I know that the input stage is working, and working rather effectively. However, it's not providing us much gain, but then again it's not supposed to. See, all it's supposed to do is provide us with a differential input signal, one coming off the negative feedback rail here and the normal input that way. All the voltage gain of the amplifier is controlled by the VAS transistor. So the next thing I'm going to do is I'm going to build the rest of the circuit up to the drivers, but not the output stage, and we'll test it again with just the drivers, because remember, these drivers here are actually an amplifier. And I did forget to mention that this is a emitter follower amplifier, but these two driver transistors actually form an output stage, albeit you won't get much voltage out of it. I should say current, really. So that's the next thing to do, is build up the rest of that circuit, bar the output stage, and test it again and see what we get. Before I do that though, I did forget to mention that the supply voltage is fairly important here. Now currently, when I've got the voltage down to around about 8 volt plus minus, we can see that it's starting to symmetrically clip. If I now wind the voltage up and then wind it all the way to the supply's capacity, which is 30 volt plus minus, we notice now that our output is sitting around 1 volt peak to peak, thereabouts. And so it'll run fine at around plus minus 17 volt, but any lower than that and it starts to flat top and flat bottom. So we know what the minimum voltage requirement for the actual input stage is. Okay, about another 40 minutes later of screwing around, I've actually got the amplifier built up to the driver stage and the self-biasing network. I've got the supply currently at plus minus 20 volt, but what I'm going to do is current limit it, and I'm going to start off at a lower voltage because I'm always nervous about powering up a circuit that I know nothing about or I've never built before, and yeah, it's always good to take a few precautions just in case I've wired something wrong. So I'll turn it on. Currently there's no unusual current draw, so I'll wind the voltage up. And I'm looking at my oscilloscope as well, and I am starting to see an output. So I'm currently on a times 10 probe, so if I back that back off, we can see it's got an output and it looks strange, but I'll up the output even more, the voltage, and there we go. All of a sudden it's now corrected itself around 15 volt. That's because if I back it off, the input stage is currently not functioning, and it has nothing to do with current limiting. So current limiting is off. As soon as I come up to 15 volt, we get a nice clean sine wave. Now if I increase the voltage to, well, I might as well go to 30 volt, we're not getting an increase in the output voltage. So I'll back it back off to about 20. And at the moment, this is not going into a dummy load. So here is my VAS transistor, which is not getting hot. One driver transistor, which is not getting hot. The other driver transistor, which is not getting hot. But we are actually producing an output, which is quite nice to see. But we're only pushing 15 volt peak to peak, so it's not going to be producing much output power. However, that's with the output stage disconnected, and I'm not sure what the input sensitivity is yet, but if I now put the driver stage into a dummy load, we'll see what the actual output voltage swing is. Okay, dummy load's connected across the output. Now again, we're only testing the drivers, these two transistors here, and they're not going to produce a lot of current, so keep that in mind. So looking at our oscilloscope, we'll turn the load on, and we actually have a significant decrease, and it's, yeah, really clipping badly. So running that directly into a dummy load is not going to help, and it does make sense, because these are, as the name implies, just drivers. So now what I need to do is build the output stage of the Darlington parallel configuration, which turns this driver stage into a Darlington transistor. And we'll have a look without including the Zobel network. Now, we all know from experience that the Zobel network will stop this from oscillating. So it is kind of important, but for testing purposes I'm going to leave it out. I'm just going to build these two transistor stages onto a heatsink with the 47 ohm, well actually 0.47 ohm resistors soldered to the pins. Okay, as Frankenstein's penis that looks, the output stage is built. I've got it connected to the main circuit board down here, and I've got separate power wires going back to the power supply for the collectors in the for the supply. There it is sitting there. Nothing's changed on this. Everything's the same. I've got the supply voltage right down and current limiting on, just in case something goes horribly wrong. Oscilloscope is hooked up across the output via a dummy load, and the DDS is still at 1 volt peak to peak, 1 kilohertz. I'll turn it on. Well, no unusual current draw. Slowly wind the voltage up. And I can't see anything on the oscilloscope yet. I'm currently at 15 odd volt. Still can't see anything on the oscilloscope. I'm at 26 volt. Still can't see anything on the oscilloscope. But currently, I can't see any output. So I'll put that back on times 1 and see if there is an output. No, there isn't. So, for some reason, I'm not getting an output. So I'll take current limiting off. Ah, there we go. We've now got an output. And we're drawing close to an amp. But we're still only getting 15 odd volt peak to peak out of it. But again, I don't know what the actual input sensitivity of the amplifier is yet. It is purported to be 1 volt, but that could also be incorrect. Now, if I select this to 2 volt peak to peak, now we have a more decent output swing. So I'll decrease that. I'll change the amplitude again to 3 volt peak to peak. We're getting 44 out of it, so it's still giving us a nice clean signal. So at 4 volt peak to peak, yeah, we're starting to clip. So I'll back that off until clipping goes away. Which is, I'm going to say around about the 3 volt peak to peak mark. Yeah, and we're currently drawing close to 2 amps, and we're pushing out 44 volt peak to peak. The reason for such a high input voltage sensitivity is because of that gain setting of 15. It really needs to be around about 23. So currently we're pushing, well, I didn't have the voltage all the way up, but I ballparked it at 3, and we are clipping at about 3.1. So as I said, we're pushing out 44.3, I think that says. 44.3. So 44.3 divided by 2 equals that. If we now do that to the power of 2 equals that, divide it by our load, we are getting roughly 61 watt out of it. That's peak, so that is quite impressive. A little higher voltage probably give you a bit more. So I'm just going to check my output stage. No, it's not getting overly hot, which is good. Drivers are reasonably cold. Bass is pretty good too. So we're going to take our RMS value now of 16.22. So 16.22 to the power of 2 equals that. Now divided by our load, 32.8 watts. So for a little circuit like that, and pretty basic power amplifier circuit like that, it is actually working quite well. And the choice of these 0.47 ohm resistors, of the degeneration resistors in the output, won't overly affect its performance. And currently, from what I can see on the oscilloscope, the signal is clean, there's no sign of oscillation, so it doesn't even really need a Zobel network, to be honest. So I'm going to go out on a limb here, and I'll say at plus minus 35 volt that this amplifier will be around about 49-50 watts average and around 70 watt peak, which is quite impressive because we've got two transistors sharing the load, so it's able to push more current. Now, with these choice of transistors, I wouldn't make the power supply any higher than plus minus 42 volts, just saying. If you want to try it on plus minus 42 volts, do it so at your own risk. The main circuitry down here will handle it just fine. Whether these output transistors can actually handle that amount of voltage, that's to remain to be said. But you can probably change them for MJ 1503s and 1504s, or 15,004s. Let's try that again. MJ 150003 and MJ 150004 respectively. And you can apply a higher voltage. I think the base collector voltage is 100. These are only like a base collector voltage of 60. So keep that in mind. So albeit that it's functioning, it's not overheating. It's running quite cold actually. So what about its frequency response at full power? Well, if I go into sweep mode, remaining stable at 44.2 volt. I'll turn the soldering iron off too. In fact, towards the higher end we're getting slightly more output voltage. Actually lower output voltage, I should say. So it starts rolling off, I would say around, we're at 7 kilohertz now, around the 12 kilohertz mark. So that's functioning. I'll take it off of that now. And in fact, I might kill the DDS altogether. Now, next thing, burning question here is unloaded. That is the amplifier with no input signal, unloaded, so it's not going into a speaker or a dummy load. What's the DC offset on the output? Well, let's find out. Just so you know, that dummy load is quite hot. It's hotter compared to the heatsink. That was sinking quite a bit of current. Okay, so with the multimeter hooked up in the voltage scale across the output now, we're going to look at its DC offset, so I'll get my hand out the way and turn it on. It's actually not a bad DC offset. We're looking at, even on breadboard, we're looking at about 90 millivolt. About 90 millivolt, which is pretty average for a discrete amplifier like that. 60 to between 60 and 90 is pretty good, but it starts falling off, as we can see, as the output stage starts to warm up and the bias changes in the output stage due to the silicon diodes. Yeah, I'm happy with that. 80 millivolt, 79 now, after it settles down, is pretty good. I'm quite pleased. This worked out better than that discrete one that I was playing around with, that 25 watt average amplifier. It had excessive amounts of DC offset, but I mucked around with the initial circuit in the first place, so that's what happens. So my penis is happy. Next step would be to hook it up to a speaker and a source of sound and just see how it sounds. Obviously it's going to sound okay compared to the frequency response of the actual test, so it should sound fine into a 15 ohm load speaker anyway. But we might as well just do it for sense of completeness. Okay, I got the amplifier hooked up to that crap speaker on the floor that I don't give a shit about. I have a 10k logarithmic pot here as a volume control connected at the input, and I'm going off to a RCA socket which is going back to the CD player. So if I turn the load on and see if it makes any rude noises. No, actually. So I'll press play, hopefully I've got the right CD. No, I haven't. We go back to disc 2. Let's try disc 1. Brilliante. That sounded actually alright, apart from the fact that that 15 ohm speaker on the floor isn't exactly a full range speaker, and its frequency response probably cuts off around about the 10 kilohertz range, so we're actually not getting enough highs coming out of it. That's why it sounded a little bit muddy. It's not the amplifier doing it, it's the speaker doing it. Plus the camera audio is also going to affect the results. But it does sound to me quite clean, undistorted. As to what its actual total harmonic distortion is, I don't know. It would be less than 0.1%, put it that way. So that's going on what I know about these generic transistors that we're using here. Of course, total harmonic distortion will also be due to layout as well. It's badly laid out, but it works. If it's laid out on a circuit board correctly, no problem. So anyway, to finish this video off, wasn't even a turn-off transient pop. How nice. Certainly a lot better than that 25 watt module I built. You turn it on and it went bang through the output. Anyway, to finish up this video, I'm going to just go through some changes I made to the original schematic, and then we'll end the video there. So to recap my test results here first, this is operating at a plus minus DC voltage supply of 28 volt. So that's 56 volt DC center tapped. And all tests done into 8 ohms. We're getting 61.3 watts peak power, and using the RMS or average value we're getting 32.8 watts respectively into 8 ohms. DC offset is relatively good at approximately 79 millivolts, and our gain equaling 15. Our input sensitivity is 3 volt peak to peak for full output power. Now I need a magnet. It's got a protective condom on it. Get rid of the protective condom. So here's our schematic. I don't know how well you can see it, but I'll zoom in on the changes. For a start, for a gain of 34, I would change this 2K2 resistor here to a 1K, and that shouldn't affect our DC offset that greatly. So giving it a gain of 34 would give it a much more lower input sensitivity, therefore giving the amplifier more headroom. Next couple of changes is this 270 microfarad 40 volts being changed to a 220 because I didn't have any 330s at 63 volts, so I used the 220 at 50 volt, and that's part of the bootstrap circuit, so that still works absolutely fine using a 220. This 56 picofarad here in the base collector junction of the BD139 driver has been changed to a 68 picofarad. Conversely, its sister down here, this 56 picofarad across the BD140 driver between base and collector, has been changed to a 68p also. Reason for that is because I didn't have any 56 picofarad capacitors. The next change here is I changed these two 120 ohm degeneration resistors for the emitters of the drivers to 150 because again I didn't have any 120s, so I just upped the ohmage, for want of a better word, resistance to 150 rather than lowering it to 100. It still works relatively okay. And our output degeneration resistors here have been changed to 0.47 ohm, 5 watts. The output devices are, that's my alarm. On the positive side, the output devices have been changed to TIP 3055s respectively from the TIP 140s. Using Darlington transistors there, would you gain any greater performance out of it? No, it just would have better current handling capabilities. And down here, the PMP devices have been changed to TIP 2955s from the TIP 145 respectively. Again, they're just standard bipolar transistors, they're not Darlington. Is there an advantage to using Darlington there? Only for greater current capability. Next change would be this 10 ohm in the Zobel network, change it to a 1 watt. It doesn't need to be 5 watts. I don't know why he chose 5 watt. He just did. It's untested, but I know it's going to function just fine with a 10 ohm 1 watt resistor there. Next, that 10 ohm 5 watt resistor in series with the output, it's gone. It's not needed. Just delete it. You'd only put that there, and it would be only a 1 watt device, mind you, if you're going to put a inductor in parallel with it. And the final addition rather than change would be I would add a 100 microfarad capacitor here and 100 nanofarad there on the positive rail and the same on the negative rail, just to give that better supply line filtering. And also the diodes originally were 1N4001s. I've used 1N4004s and the circuit is working just fine. The only difference is The ones are a reverse breakdown voltage of 600 volt, and the 4004s have a reverse breakdown voltage of 1000. Not that that particularly matters in this sort of arrangement. So, all in all, that little amplifier does perform quite well for its simplicity. So I'm happy with the results. And next question is, what am I going to do with it? Well, I'm probably going to replace that 25 watt average module that I was going to put in my mixer amplifier to this one, which means I have to design a circuit board for it. I just wanted a little bit more output power capability, and well, it doesn't have a VBE multiplier, it's not adjustable biasing, so you can just plug it in and go straight away without having to do any messy setup arrangements. The original circuit said it could go to 260 watts RMS. Yeah, no way. No way. Not at plus minus 45 volt. No way. Even with Darlington transistors at the output stage. No. That's not going to happen. So that's what I'm planning to do with it, and we'll come and revisit this again later once I've moved. So this is going to be the last video of the Astro 30's electronics lab in this house anyway, and I'm going to spend the next 3 days packing stuff, pulling the lab apart and getting ready to move it. So I'm going to leave this video here, and if you enjoyed it, please remember to rate, comment and subscribe below, and thank you for following me and subscribing. And if you're new to this channel and haven't subscribed, just remember to subscribe down below, when you can always rate and comment. Always like reading comments, negative or positive. Anyway, this is the Astro 30 saying, see you later. Happy Class AB amplifier. I have no idea why I keep saying shit like that. It's just absolutely stupid.